Today we will be going over the titration of a strong base with a strong acid and how to go about calculating the pH of the solution at different points of the titration. Our example will be dealing with the following: a 30 milliliter sample of 0.01 molar NaOH solution titrated with a 0.05 molar HCl solution. Before we begin, some important things to remember are that titrations involving strong acids and bases generate water and salts as products, since these compounds fully dissociate in aqueous form. Here are the general dissociation reactions of a general strong base and acid, as well as the titration curve for this type of titration. Now that we have a general idea of what we will be working with, we can begin. In this example, we are asked to find the pH of the solution before the addition of acid. Now remember, since no acid has been added, there is no free hydronium, so our pH must be calculated from the pOH. The pOH can be attained from the concentration of hydroxide. So in this case, since the base we are using fully dissociates, this indicates that the concentration of NaOH is equal to the concentration of hydroxide. So the concentration of hydroxide is equal to 0.01 molar. Now this concentration can be input into the pOH equation, which is simply the negative log of the concentration of hydroxide. So this gives that the pOH is equal to the negative log of 0.01, which is equal to 2. So now that we have the pOH, we can find the pH using pH is equal to 14 minus pOH. So if we plug this in, we get pH is equal to 14 minus 2, which is equal to 12. So the pH of the solution before the addition of acid is 12. So this makes sense because currently there is no acid present and only base. So 12 is very basic of a pH. So here's where we would expect the pH value we calculated to be located on the titration graph. So it would start here at the top because our pH is high due to there only being base, and since we still have not added any acid. Now let us look at a different scenario. So here we will be calculating the pH after adding 4 milliliters of acid. So the first step is to write the chemical formula of the reaction. So as we see here, the products formed are a salt and water. Second step is to calculate the millimoles of hydronium and hydroxide. So we do this by multiplying our molarity by the volume of each individual acid and base. So in this case, the concentration of hydroxide is equal to 0.01 molar times the 30 milliliters, which gives us 0.3 millimoles of hydroxide, and our hydronium concentration is equal to 0.05 molar times 4 milliliters, which were added, which is equal to 0.2 millimoles of hydronium. So now the third step is finding the remaining millimoles of hydroxide or hydronium. So in this case, we only have 0.2 millimoles of hydronium, or H+. So this would be our limiting reagent. So this is what we will be subtracting from our excess, which in this case is the 0.3 millimoles of hydroxide, or OH minus. So this would give us 0.3 minus 0.2, which leaves us with 0.1 millimoles of hydroxide left. Now the fourth step is to calculate the new concentration of hydroxide. So we have to remember that we started with 30 milliliters, but we added an additional 4 of acid. So this changes the total volume, which thus affects the final concentration. So using the new millimoles of OH that we found, so what remains, and we divide it by the new total volume, which is the 30 plus the 4, we get that the final concentration of the hydroxide is equal to 0.00294 molar. So now that we have the concentration of hydroxide, we can calculate the pOH, which we can then use to find the pH. So since the concentration of hydroxide is equal to 0.00294, we can plug this in to the pOH, which is equal to the negative log of this concentration, which gives us 2.53. Now, to calculate the pH, we can subtract the pOH from 14, so in this case, 14 minus 2.53, which is equal to 11.4. So the pH of the solution after having added 4 milliliters of acid is 11.4. And this makes sense since now we have added some acid, so this would, as expected, decrease our pH. So we started with a pH of 12, and now we're at a pH of 11.4. So the addition of a little bit of acid has lowered the pH. So here's where we would expect the pH value we calculated to be located on the titration graph. Our third example involves the addition of 6 milliliters of HCl to the NaOH. The first step is to write the chemical reaction, which we have previously done. The second step, as before, is to find the millimoles of hydronium and hydroxide using the molarity and volume. So here in this example, we have 0.3 millimoles of hydroxide and 0.3 millimoles of hydronium. So now we have to calculate the remaining millimoles of hydroxide or hydronium. In this case, since the amounts are equal, we are left with no remaining hydroxide or hydronium. Since there are no moles of hydroxide or hydronium remaining, we must recognize that all of the free hydronium and hydroxide was converted to H2O, water. So at the point where the concentration of hydronium is equal to the concentration of hydroxide in a given sample is referred to the equivalence point. And at this point, all acid and base is neutralized. Since all that is remaining in the solution is water and the salt, but the salt has no effect on pH, the pH of water is used. So since water has a neutral pH of 7, the solution of the pH of the solution after adding 6 milliliters of acid is 7. So again, this is at the equivalence point. So here's where we would expect the pH value we calculated to be located on the titration graph. Our final example is the addition of acid, which would be past the equivalence point. So in this case, the addition of 10 milliliters of HCl. So like before, we start by writing the chemical formula of the reaction, followed by calculating the millimoles of hydronium and hydroxide. So again, we use the volume and the molarity. So in this case, we have 0.3 millimoles of hydroxide and 0.5 millimoles of hydronium. Again, we find the remaining millimoles of either hydroxide or hydronium. So since our limiting reagent in this example is the hydroxide at 0.3, we will subtract this from the 0.5 millimoles of hydronium. So we're left with a remaining 0.2 millimoles of hydronium, or H+. Like before, we have added acid, so the volume changes, and the concentration of hydronium also changed, so we have to calculate the new concentration. So the new concentration of hydronium in the sample is 0.2 millimoles of hydronium divided by the initial 30 milliliters plus the 10 milliliters of acid we added, which gives us a final concentration of 0.005 molar. So since this concentration is already the concentration of hydronium, we can calculate the pH by simply plugging it into the pH equation. So our pH is equal to the negative log of the 0.005, which gives us 2.3. So the pH of the solution after having added 10 milliliters of acid is 2.3. So this concentration makes sense, right? Because at this point, we're past the equivalence, so there's no more hydronium or hydroxide, OH, present. So all that is present is either water, salt, or free hydronium. So since there's more acid than of the other things, our pH is much lower. So we started from 12, and now we're at a pH of 2.3. So here's where we would expect the pH that we just calculated to be located on the titration graph. Thank you for watching. Hopefully this tutorial has been helpful and allowed you to have a better understanding of titrations of strong bases by strong acids.